Hi everybody. So now we're going to take the ideas that we talked about in the introductory video and try to formulate them in a precise way in higher dimensions so that we can see what the problem is that we need to solve if we want to try to find a hyperplane which separates our two sets of points, one the positive points, the green points, and the blue points, or the Adelie penguins and the Gentoo penguins, but now in higher dimensions. And so the goal of this video is really just to formulate the problem, and then it's going to take some new ideas in order to see how to solve the resulting optimization problem. So let's get started. We're in our standard situation where we have an n by k data matrix, the rows of which are samples. There are k features. We also have an n by 1 target vector y, whose entries are plus or minus 1, which distinguish the two classes that we're interested in. And we're dealing with a binary classification problem where we're trying to predict which class a particular data point ought to belong to based on the training data that we're given. And just to remind you one more time, the strategy is we have a bunch of points in Rk corresponding to the rows of our data matrix. Each one has k entries. We think of it as a point in Rk. We think of the points labeled +1 and the points labeled -1. We hope that it's the case that we can find a hyperplane which passes between those two sets, and then we decree that everything that lies on one as our classification algorithm, if you lie on one side of the hyperplane, you're a plus point. If you lie on the other side of the hyperplane, you're a minus point. So before charging ahead, let's think a little bit about hyperplanes. An affine hyperplane in Rk is given by an equation of the form f of x equals 0, where f of x is a degree 1 polynomial. So you have k coefficients, w1 up to wk, and a constant b, and you set f of x1 up to xk to being w1 x1 plus w2 x2 and so on, plus wk xk plus b, and you set that equal to 0. F of x equals 0 is your affine hyperplane. It's called affine because it doesn't necessarily pass through the origin. In linear algebra, you often think about hyperplanes that pass through the origin. The effect of the b is to shift the hyperplane so that it doesn't necessarily pass through the origin. We're going to work in vector notation and use ideas from vector geometry. So we're going to express the coefficients as a vector in Rk and write our degree 1 polynomial in vector form, where f of x is w dot x plus b. W is the dot x is the usual dot product. So here x is x1 up to xk is the variable, if you like, and w, which is w1 up to wk, are the coefficients. And b is just a constant, w dot x plus b. Okay, so let's recall sort of a few basics about hyperplanes. The first thing is the reason we're interested in them. Namely, if you have a hyperplane in Rk given by this vector equation f of x equals w dot x plus b equals 0, then it divides space up into three regions. There's a region where the function is positive. There's the region where the function is 0, which is the hyperplane itself. And then there's the region where the function is negative. And these two big regions are called half spaces for obvious reasons. And so our hope is to get the plus points in one half space and the minus points in another half space. The vector w has a geometric interpretation. It's the normal vector to the hyperplane. So here's our hyperplane. Here's w. And to see that, if you choose any 2 points, x1 and x2, in your hyperplane, and look at the vector joining them, which is x2 minus x1, and take its dot product with w, well, you get w dot x2 minus w dot x1. But since these lie in the hyperplane where f of x, which is w dot x plus b, equals 0, we know that w dot x2 equals minus b and w dot x1 equals minus b. So w dot x2 minus x1 is 0. In other words, W is perpendicular to any vector which lies within the hyperplane given by the equation f of x equals 0. And finally, if we want to know the distance of a point to a hyperplane measured perpendicular to the hyperplane, so here's our f of x equals 0. Here's our point P. If we're interested in this perpendicular distance, d, it's equal to f of p over the norm of w. To see that, we want to take the vector p minus x1, and we want to project it onto the normal direction. So we want to take the norm of p minus x1 times the cosine of the angle theta. But that is w dotted with p minus x1 over the norm of w, using the usual properties of the dot product. And that in turn is equal to w dot p minus w dot x1 over the norm of w. But w dot x1 is minus b, because x1 lies on the hyperplane. So therefore, this is equal to w dot p plus b over the norm of w, which is f of p over the norm of w. Now, our hope is that there is a hyperplane which separates our data into the two classes, and we're going to introduce a definition. We're going to say that the data is linearly separable if there's a vector w and a constant b, so that on the one hand, for the plus points, f of x, if you plug in a plus point, you get a positive number, f of x equals w dot x plus b is bigger than 0. And if you plug in a minus point, w dot x plus b is less than 0. And if you can do this, if w and b have this property, then this is called a separating hyperplane. So here's the very familiar picture at this point. Here we have w dot x plus b is bigger than 0. Here we have w dot x plus b is less than 0. So the data is linearly separable if there is a separating hyperplane. If there is one, there will typically be many, because you'll be able to tilt it a little bit. But there isn't always a separating hyperplane. You can imagine data points which are sort of mixed together so that no matter how you draw a line between them, you can't separate them. So this is a real property. Sometimes it holds, sometimes not. So we need some kind of way of telling if our set of points is linearly separable. And so we're gonna do a little analysis of this point. So first, let's let a plus be our positively labeled points and a minus be our negatively labeled points. And the question we want to ask is, can we find a b and a w so that w dot x plus b is positive on the positive points and negative on the negative points? And I guess the main point of the proposition I'm going to prove is that it's really all about the w. We can sort of put the b a little bit in the back of our minds. And it turns out that a plus and a minus are going to be linearly separable if you can find a w which satisfies this property, that the maximum value of w dot x on the negative points is smaller than the minimum value of w dot x on the positive points. And to see why this is true, let's go back to the original definition. So we need w dot x plus b to be bigger than 0 for all x in a plus. Well, that means that that minus b is less than w dot x for all x in a plus. Or in other words, minus b is less than the minimum of w dot x. Because if you're less than every element of a set, it's a finite set, then you're less than every element of it, then you're less than the smallest element of it, and vice versa. And similarly, if you want w dot x plus b to be less than 0 for x in a minus, then you want minus b to be bigger than w dot x for all x in a minus. And so you want minus b to be bigger than the maximum over x in a minus of w dot x. And if you look at these two conditions, if you have to have a number which is smaller than this number and bigger than that number, it had better be the case that the maximum over x in a minus of w dot x had better be smaller than the minimum of x in a plus of w dot x, because you've got to fit a minus b in here. And if that condition didn't hold, it wouldn't be possible to do that. On the other hand, if the inequality does hold, then you can choose any minus b you want in that range, in that gap between these two numbers. And if you work this all backwards, you'll see that you'll have the condition that you need. So it's enough, if you want to know if your set is linearly separable, it's enough to look at the w dot x's as w varies. And then if you can find such a w with this inequality holding, then there's going to be a lot of b's, an infinite set of b's that are going to work, that you choose between, you choose minus b between these two endpoints. So given the fact that we're interested in these numbers, let's let b minus of w be the maximum value of w dot x on the negative points, and b plus be the minimum value of w dot x on the positive points. These are functions of w. And our sets are going to be linearly separable if b minus is less than b plus. And if b minus is less than b plus, you can choose minus b between b minus and b plus and let f of x equal w dot x plus b, and that will be a separating hyperplane. Now, let's try to look at this in a more concrete situation. So, remember the penguins. This is the data set of penguins that we looked at, and we're going to do some analysis of this picture to try to figure out what it is that's going on. So, let me remind you, we had green dots and blue dots were our two classes, and I had eyeballed a line that separated them. And the line that I had eyeballed was y equals 1.25x plus 2. And in order to work with this, we need to put this into our vector form. And to do that, we have to write this as 1.25x minus y plus 2 equals 0. In other words, w is 1.25 minus 1, and b is 2, and f of x is w dot x plus b equals 0. That gives our line. But we have to be a little bit careful here, because what are the plus points and what are the minus points? Well, if we want to use this as our hyperplane, then f of x bigger than 0 means that 1.25x minus y plus 2 is bigger than 0. In other words, y is less than 1.25x plus 2. In other words, these are the plus points down here, the blue points. And the green points are the minus points. And the vector w, which is 1.25 minus 1, points this way. Okay, so the numbers that we were interested in here were the b plus and the b minus. So b minus, just to remind you, is the maximum value of w dot x over the minus points. Well, w, remember, increases as we move from the upper left to the lower right. So if we want to find the maximum value of w dot x, we're going to go this way, and w dot x is going to be increasing and increasing and increasing. And because remember, it's w dot x, so it's the projection of x into the w direction that matters. And so the largest value of that is going to occur at the point which is the most in the w direction that you can get and still be green. In other words, it's going to be this point right here. And if you take the line which is of the form w dot x plus b, but which passes through this point, then this green line right here is f of x is w dot x minus w dot x minus equals 0. This is the point I'm calling x minus. It's the extreme point in that direction. And I had worked this out. That line, the green line there, is y equals 1.25x plus 2.003, but you have to put that in vector form. So that's f of x equals 1.25x minus y plus 2.003 equals 0. In other words, w dot x minus has to be minus 2.003. That's the maximum value. W dot x minus is minus 2.003. And now, if you keep going and you continue this way, still traveling in the w direction, then b plus is the minimum value So since as you go this way, w dot x is going to keep growing, the minimum value of that w dot x is going to occur here. This is the point I would call x plus. And the line that passes through x plus, I worked out, is y equals 1.25x plus 1.998. And if you repeat this little analysis here, and you take into account the sign changes, what you find is that, so I should have said here, this is b minus. What you find for b plus, which is the minimum value of w dot x over the plus points, is minus 1.998. And as you see here, b plus, which is minus 1.998, is bigger than b minus, which is minus 2.003. So as we wanted, I mean, these points are linearly separable, and we do find that b plus and b minus are in the correct order. And the other thing I just want to point out is that these points, which are the extreme points, are called support points. So x plus or minus here, these are called support points. And these hyperplanes that pass through them are called supporting hyperplanes, the blue and green lines. And the idea here, if you want to think about it, is that what we've done is we've picked a direction. And we've now looked at this family of parallel lines that pass through all the plus points. And we've pushed those lines as far towards the minus points as, or I guess in our case, we're pushing from below. We've taken all of these lines and we've looked for the one which is closest to a green point but runs through the blue points. And similarly, the one that runs through the green points but is closest to the blue point. And when we can't move any farther, because doing so, we would cross into the other guy's territory, so to speak, the points at the boundary are called support points, and the hyperplanes through them are called supporting hyperplanes. And as long as these b plus and b minus are in the right order, we know that any number that we pick between those two numbers, so any line of the form y equals 1.25x plus b, where b is between 1.998 and 2.003, is going to give us a separating hyperplane that points in the w direction. Great. So just to drive home this notation here, suppose you have a collection of points in Rk. Then a supporting hyperplane is a hyperplane which has the property that all of the points lie on one side of it, and at least one point lies on it. So it's as far this way as possible. And there's really two, you have to give the definition in two forms, because it's either everything's on the positive side except that something's on the hyperplane, or everything's on the negative side except that something's on the hyperplane. But the important point is that everything's on one side, and you can't move it any farther because one point's on it. If you moved it any farther, you'd leave a point on the wrong side. That's called a supporting hyperplane. So now let's go back to our original question. As we saw, when we move we can always get we have our vector W, and we can look at these points where we figure out B plus and B minus given W. We figure out B plus and B minus. These are these maximums and minimums. And then we get these hyperplanes, F plus, which is W dot X minus B plus, and F minus, which is W dot X minus B minus, which pass through the supported points X plus and X minus. Then we're in this situation. Here we are. Here's these two parallel hyperplanes with the same normal vector W, and we have a point X plus here and a point X minus here. The perpendicular distance between those two supporting hyperplanes is called the geometric margin. It's called the geometric margin for the direction W. And that distance is given by this formula. So yeah, I should mention here, right, that B plus is W dot X plus, and B minus is W dot X minus. So how do you compute this perpendicular distance? Well, we've seen this now a whole bunch of times. You take the vector from X plus to X minus, you project it onto W. So you take W dot X plus minus X minus. You divide by the norm of W. This gives you the projection of X plus minus X minus into the perpendicular distance. And using B plus and B minus, this is equal to B plus of W minus B minus of W over the norm of W. So once you pick a direction W that separates it, you find these supporting hyperplanes, you take the perpendicular distance between them, and that gives you the geometric margin for that vector W. And if you want the sort of best separating line in that direction, you should take the midpoint. And this is the equation of the hyperplane that passes in between these two supporting hyperplanes, which are kind of as close together as you can move them. Or that maybe a better way to put them is you can't make them any farther apart in this direction, or you would cross into the forbidden zone where you have positive or negative points on the wrong side of them. Okay. But the problem we have is to find the largest possible margin as W varies. And that's called the optimal margin problem. So now what we want to do is not just find these points X plus and X minus, but we want to let W vary. So as W varies, we're tilting these lines. We're going to bump up against points in certain places which prevent us from kind of moving any farther. And so we define the optimum margin, tau of A plus and A minus. A plus are the plus points, A minus are the minus points, to be the largest geometric margin as W, the vector which gives the normal to the hyperplane, or it's kind of the direction, as W varies. And if you can find that optimum, the biggest possible margin, then you take the hyperplane in between, in the midpoint of that margin, and that's your classifying hyperplane. So now we have an optimization problem. It's a complicated one. Find W so that this gap between the supporting hyperplanes is as big as possible, given our set of points. Now, before I wrap up this, and because we'll have to talk about how you would solve that problem, I just want to disabuse you of one naive thought that you might have had, and which I had when I first thought about this, which was, why go through all this craziness? Isn't this just the closest point between the two sets? And sometimes it is. I mean, for instance, if if you take points that are sort of, here's my minus points maybe, and here's my plus points, it seems pretty reasonable that what I should do is take the closest points, draw a line between them, and take maybe take the perpendicular to that line, and that would be the optimum margin. And it's true that that is sometimes what happens, but it's not what's true in general. So in this proposition, what's true is that the closest distance between the two sets is always bigger than or equal to the margin, but it can be bigger. And so let's see why that's true. Let's prove the one direction, and then we'll worry about the other direction. I'll show you a counterexample to explain why what you might think of as the more naive picture doesn't hold. So let's just remember what's going on here. So we have our F is our optimal hyperplane. So and we have our support points. So here, let's say or W maybe gives our optimal hyperplane. So we have F plus is W dot X minus W dot X plus bigger than or equal to 0. That's the supporting hyperplane. In other words, W dot X is bigger than or equal to B plus for all X in the positive points. And W dot X is less than or equal to B minus for all X in the minus points. So let's take the negative of this. Negative W dot X is bigger than or equal to negative B minus for all X in the negative points. So adding these two equations together, where we take X to be a positive, let's say take a positive point here, so we would get W dot P plus, and put in a negative point here, minus W dot P minus, is always going to be bigger than or equal to B plus minus B minus. Where P plus is an A plus and P minus is an A minus. You can take any point that you want there. Okay, well that means that W dotted with P plus minus P minus is bigger than or equal to B plus minus B minus. And the distance, the perpendicular distance as usual, is gotten by dividing by the norm of W. So we would have that the distance, the perpendicular distance from P plus to P minus is equal to W dot P plus minus P minus over the norm of W, and that's bigger than or equal to B plus minus B minus over the norm of W, which is our margin. So the perpendicular distance between any 2 points is always bigger than or equal to the margin. And the true distance is always bigger than or equal to the perpendicular distance. Because this has a cosine of theta in it. This is the length of P plus minus P minus times the cosine of the angle between P plus minus P minus and W. And this is just the distance from P plus minus P minus. So the closest points, the distance between the closest points is always bigger than or equal to the margin. But it's not always equal to the margin. And here's a picture that shows what goes wrong. My blue points are one set. These are like the plus points, and these are the minus points. And you'll notice that the closest blue point to a red point is measured here, along these hypotenuses, so to speak. But the margin, the separating line, the distance is much closer. And you see that you can't really do anything. This line here, it's got to go through these 2 points. Otherwise, if you try tilting these lines, you'll find that they get closer together. In other words, if you were to take something like this and this margin would be smaller than this margin. So the margin gets bigger up until these lines are vertical and it passes through these 2 points. Then you can't go any farther because you're hitting 2 points, so it's rigid, but that margin is still quite a bit smaller than this closest distance. So the margin is a subtle thing. It's not just the closest distance between the 2 points. And in later lectures, we're going to look at it much more closely.